All right, I wanted to do a quick follow-up video on the idea of two curves being homotopically equivalent. This is something that I feel like I just need to say a little bit more. Maybe I didn't explain it very well the first time. Either way, I want to say a little bit more now. So what I want to do is I want to take a curve, or take a region rather. So take some open connected set. And when I draw these dotted points, I mean, of course, that this is the dotted points are the boundary, and then the set we're talking about is actually this open set that's its interior, okay? And I don't care if it's, maybe it's missing part of the inside, so maybe it's got something like that. It doesn't matter, but just take a region, so an open connected set, and then consider a curve in this region. So let's say you could have a curve that's, something. It can be as weird as that. It can be just a normal circle or something like a circle. Maybe it could even be a circle that goes around. This kind of looks like an annulus. An annulus in complex analysis is a set. So it's the set of complex numbers where, say, z is between 1 and 2, right? So it's basically a circle with a circle missing inside. That's an annulus. So it looks like a ring. So that's, this is the place where we're looking at this. So this is just our region G. And what I want to do is I want to think about, so let's call this region G. And I want to think about what are some other curves that are equivalent to this green curve under homotopy. So what are some curves that are homotopically equivalent? And I want to remind you of the rules that we're allowed to play. So what we're allowed to do with these curves is we're allowed to stretch them. We're allowed to shrink them. You can kind of rotate them, so like change them continuously that way. You can even take one end and twist it. The only few things that you're not allowed to do is you're not allowed to break it. Okay, so you're not allowed to break the curve. You can't split it at one point and then move that part and then sew it back together somewhere else. Okay, so that's not allowed. The curve has to stay completely within G at all times. So you can't take this green curve. Let's see if I can do it. You can't take this green curve and you can't move it so that it's outside G. And that's not going to work. Okay, so it's got to stay in G the whole time. And then the other thing that you're not allowed to do is you can't change the orientation. So this is a positively oriented curve, meaning that it's going this direction. So its interior is to its left as it traverses around the curve. That's what positively oriented means. If you were to imagine walking around this curve, if you were to stop at any point and look to your left, okay, then you would be inside the curve. That's positively oriented in a nutshell. Okay, but those are the rules. So you can continuously move the curve. You can stretch it, shrink it, but it has to always stay within G. You can't change its orientation, and you can't cut it and then move it and then sew it back together. So for example, if you were to take and say remove a point here, and then all of a sudden, if you were to remove some of these or just break it at a point and then kind of move it around, you could, if that was allowed, which it's not, but you could, change it to a curve over here, right? But that's not allowed. So it turns out that this curve is kind of stuck with this region here, always on the inside of the curve. There's nothing that you can do about that. No matter how clever you are, you're never going to be able to get this curve so that this little missing region of G is not inside our curve. Let's call our curve gamma. Okay, so let's say this is gamma. So that's homotopy. Now, the homotopy is dependent on the underlying region G itself. It's also dependent on gamma. So if I were to have a different curve gamma, so let's say we were to take gamma and maybe we consider this curve here, okay, or something like it. You could take that green curve, okay, so this is our gamma now, and you could contract it to a point. So what that means is that you can take this curve And you can make it as small a circle as you want. In fact, you can make it a circle with radius 0. You can make it a single point. That's what a contractible curve means. Okay, so when we say gamma is contractible, we mean that we can homotopically translate it to a single point. That's in contrast to what happened before. There's no amount of work that we could do to take this curve gamma and contract it to a single point, because like we said, this missing these set of complex numbers that are not in G but are inside this circle here. So remember, G is just the stuff in here and in here and in between. Okay, so in particular, this middle region is missing. And this middle region is always going to be inside gamma based on the rules that we're allowed to employ to manipulate gamma. Okay, so that means that gamma is not contractible to a point. No matter how hard you work, the smallest that you can get gamma, you can't even actually get gamma on this border here because that border is not in G, but you can get arbitrarily close to it. So if you were to zoom in, you could contract gamma so that it's, you know, somewhere over here. You could get arbitrarily close to that border. It would have to keep the same orientation, but that's as close as you can get to contracting gamma to a point. Okay, so the last piece that I want to talk about is that we often use these ideas of homotopy when we're talking about a function. And so, you know, you're talking about a function like, let's say we have, I'm just making something up here, but let's say that you wanted to integrate over a circle of radius 2, you want to integrate 1 over z times z minus 3. I think there's something like that in one of the homeworks. Maybe there's an e to the z up top. It doesn't matter. And what you want to do is you want to think about what is a region that contains this positively oriented circle. In any open region that contains that circle will do. So what we're going to do is let's graph this. So we have this, our integrand is going to be, well, the denominator of the integrand is going to be 0 when z is 0 and when z is 3. Okay, so those 2 points are missing. And otherwise, your region G can be really any open set that contains the curve. So here we have C02. So here, I just want to be careful. I don't want to use green, but let's just look at the circle centered at 2 positively oriented. Okay, so it'll look something like that. And again, positively oriented means that it's going to go that way. And then your region G can be any open set that contains this curve. And I think in this particular case, it's convenient to construct a region G. I mean, you always want to make everything work for you as much as possible. What I mean by that is that people often say math is for the lazy. What they mean by that is that if you can make really efficient choices in math, then your life gets much easier. So for example, if this is your region G, I don't even care, call it a circle centered at 0 of radius, say 3/2. The point is that we found an open set G that contains our curve gamma that excludes one of the trouble points. And what that means is that for this particular function, we don't have to worry about what happens at 3. Okay, and so we just don't need to worry about that. And so all we really have to worry about is this curve here. Okay, so so again, this region G that we're talking about, I need to go back. I need to backtrack what I said. G can't be the circle centered at 0 of radius 3/2. It can be if we exclude, of course, we can't have anything defined at that origin. Okay, so that's the problem, is that this curve is not contractible. This red curve is not contractible to a point because you're missing this point inside. And so just like before, you can get arbitrarily close to that point. You can make a circle with as tiny a radius as you want, but it's got to have a positive radius because you're missing this point. This point can never be, it's always going to have to be inside gamma. So gamma is going to have to be some curve where that point is inside gamma. So that means that this red curve, which let's call this gamma. So this red curve is not contractible to a point, and therefore you have to do something like Cauchy's integral formula. But Cauchy's integral formula works out super nicely. Since we don't have to worry about what happens at 3, we can think of this as the integral of 1 over z minus 3 all over z dz. And we're integrating the circle centered at 0, radius 2. And this is going to be 2 pi I times whatever our function is up in the numerator at 0, because this function is holomorphic on g, because g doesn't include 3. And so you can take this 1 over z minus 3 quantity, let me try that again, 1 over z minus 3, and plug in z equals 0, and you're going to end up with negative 2/3 pi I. That's what this integral would work out to. Okay, so that's all these ideas together. I hope this video is helpful. If there's still further questions about homotopy, please let me know.